All right. Any questions on Appendix B with the absolute value notation? Usually we will not just go around the room and read answers, but I've got this solutions manual here if you ever want to come in the morning or at lunch or sometime and check over some answers if you're unsure. But any difficulties with those things? Okay. In the other class, we talked about two things. This was number 22, negative pi to pi, and so it's x minus the middle, less than or equal to the radius, so it's like this. The question came up, is it always less than or equal to? Is it always less than or equal to? And that is the case as long as you're doing a closed interval like an in-between kind of thing. Okay, and I don't know if you guys remember this, but kind of work this through in blue here. If you have x minus 2 bars and then it was pointed this way, so when I take off the bars, we did this yesterday, so I got x minus 2 greater than 4. And do you remember how you decided whether it isn't, in some problems it's and, in some problems it's or? Remember that? There's some problems where your graph is going to look like this, and then there's some problems where your graph is going to look like this. Right? I mean, that was the thing with absolute value problem. Okay? And one's an and, because it's everything this way and this way, so it's what's in both, and this is or, it's either this or it's this. Okay? Well, this is an or. And when it points this way, it's an or, and when it points the other way, it's an and. So on this one, it's an and kind of situation when it points that way, and in this case, it's an or. Okay? Yeah.
Okay, so when you didn't have the closed brackets, you had brackets.
I made a mistake. I didn't mean a closed interval. What I meant was an in-between interval.
Okay.
So when it's one of these situations, it's an interval. Yeah. So the closed or open bracket just means it's the dot for it. Right. Yeah. So I misspoke when I said closed interval. What I meant was an in-between interval. So if I finish out a problem like this, it says x greater than 6 or x less than negative 2. So if you graph that, greater than 6 would be this way, and less than negative 2 would be this way. And quite honestly, in calculus, we just don't deal with intervals like that, right? We deal with intervals where it's in between, where it's between negative pi and pi, that kind of thing. Because we're always looking at functions and saying, okay, here's this function, x squared, and we want to look at it from 2 to 7. And we're going to look at that piece of it. And so that's the intervals we talk about. So we rarely deal with absolute value problems that have a greater than. They're almost always this way. Now, interesting story, my high school teacher used to, this is how I remember it, and which one's and which one's or. He used to tell us that when it's pointing this way, if the bars are over here, you can write the word and in there without any problem. But when it's this way, if you try to write the word and in there, there's no room for the D. I swear to God, that's how he taught it. And I remember to this day, 30 years later, I still remember that. So whenever I see one right this way, I say, okay, that's an or. Okay, and I see one this way, well, that's an and, because there's room for the D. You know, so anyway, of course, that only works if the bars are on this side. Yeah. But not a big deal. To be honest, the work we have to do here in section C, Appendix C, is much more important. So let's move on to that, Appendix C. Any questions on any of those?
For a perpendicular line,
Yes.
the slope would be opposite
Opposite
reciprocal.
reciprocal. So if the slope is 2, then on the perpendicular, the slope would be negative 1/2. Negative 1/2. Opposite reciprocal. Okay. Now, Jeremiah, one of the things I told the group yesterday is when we're writing an equation of a line, I really, really want you to memorize this point slope form of a line. So if you know a point and you know the slope, this is the equation of that line. Okay? Now, yesterday we were talking about, or yesterday and Monday also a little bit, we were talking about that door swinging open problem. We were talking about instantaneous rate of change. Oops. Okay. We're looking at Appendix C, everybody. Questions in Appendix C. There weren't really any questions in Appendix B with the absolute value. Nobody really had any there. Now, some of you that just came in had some concerns. We can go back to it in a minute after we're done with this. Okay, so we're looking at Appendix C and we're talking about the line. So I was just reminding everybody that yesterday we were talking about instantaneous rate of change, and with the door swinging open. And what we wanted to know is how fast is this swinging open at 1 second? And now, of course, you guys said that was slope, right? The steeper it is, the faster it's opening. And so how steep is it? But the thing we didn't really talk, or we talked a little bit about, is slope really only applies to lines. Slope, when you've got a line like this, and you've got a couple points, or 3 or 4 points, doesn't matter, take these 2 points and do the slope, or take these 2 points and do the slope, and pick any points you want, and that's the slope of the line. But here we only have 1 point. And so what I'm trying to show everybody here is, on Appendix C, why is it so important that we memorize this equation of a line business? Because as we go through the year, we've got this graph like this. It's a curve. How do we find slope on a curve? You can't find slope on a curve because the slope's always changing, right? You can't do slope on a curve because the slope's always changing. So when we talk about wanting to know what the slope is at this point right here, what we're really saying is, what's the slope of that tangent line? Let me say that again. When we ask the question, what's the slope of this curve, what we're really saying is, what's the slope of the line that would be touching the curve right at that point? Does that make sense? So right over here where it's steeper, that line would be steeper. And right up here where it's kind of flat, the tangent line would be flat. So probably the most common question on the AP test is, find the equation of the tangent line, to this function at this point. You're going to see that question over and over and over again. Find the equation of a tangent line. Well, this is how you find the equation of any line, right here. You need a slope and you need a point. So let's think about that. Well, the point will be easy, because if they tell me to find the equation of the tangent line at point x equals 2, plug 2 into the function, that's my point, so that's easy, so they'll give me that. All I need is a slope. Well, of course, that's the big dilemma. That's what we talked about the last 2 days. How do we do slope with 1 point? We can't. We need what for slope? 2 points. So what did we do? We picked 2 points really close, like 0.9 and 1.1, right? Remember that? But now let's think about what that means. Those 2 points that we picked were on the curve, right? They were on that 200x, 2 to the negative x. Remember that curve for the door opening? When we plugged in 0.9 and 1.1, we plugged those into that curve function. They're not on the line. The only point that's on the line is that 1 point where it's touching. So when we picked these 2 points and did the slope, we were doing that slope right there. Right? And remember, we were getting 30 point whatever. Now, isn't it reasonable the slope between those 2 points is probably close to the slope of that line, though? Doesn't it look almost parallel, right? You pick 2 points on either side, get them really close. Chances are that the slope of this line is the same as the slope of that tangent line. That's the whole idea. So that's how we're going to get this slope. I mean, we're going to have, oh, look, I'm on the wrong page. Anyway, so when we want to write the equation of a line, we need a point. Well, okay, that's that point right there. And we need a slope. Well, so far all we know about the slope is we'll estimate it or pick 2 points really close together. But then we'll have our slope over point, and we'll plug that in, and there's our equation of our line. Okay? So that's the type of problem we'll be doing where we have to write the equation of a line. So we have to do it a lot. A lot. Okay, so with that intro, any problems in Appendix C? Any at all? Any problems in Appendix C? Yes, right. 31. We got the book out? 31. Okay, perfect. So on 31, it says find the equation of the line that goes through negative 3, 1. So there's our point. So that's going to go in. See, all year long, you're going to see me do this. I'm going to say, okay, they want me to write a line. They want to write me an equation of a line. So I'm always going to think back to this. I'm going to say, okay, here's the things. I need these 3 pieces. So they gave me the point, so that's easy. So that'll make that negative 3, and that'll be 1. Right? Of course, minus a negative, that's going to turn into plus positive. And now I'm just missing my slope, correct? And it's a perpendicular line. Now, we just mentioned this a second ago, but you guys haven't got that yet. What's the slope of the line they gave? 5. What's perpendicular to that? Negative 1/5, absolutely. So you put it negative 1/5 out in front, and you can stop right there. I do not care if you go any farther than that. Okay? But if you want to simplify down, go ahead. But if you do simplify down, don't screw it up. Don't make a mistake. Okay? All right. There you go. What else? Yes. Point slope form right there. So, again, you're going to hear me say this. It's going to say write the equation of the line. I'm going to say, what do you need to write the equation of the line? And you're going to say point and slope. You need a point and slope. What do you need to write the equation of the line? You need a point and you need a slope. And you're going to stick it into that right there. You need a point and you need a slope. That's what you need to write the equation of the line. Point and a slope. Put it into there and you got it. Okay, so that's Appendix C. Now, somebody did mention in the other class, they asked about 25 where it said justify. Okay, what did you have? You had y equals 2/3, what was it, x minus 1 plus 2, I think, was one version you could have had of that. And then you're supposed to tell if 2 pi is on that. So sometimes your justification or your explanation is kind of your work. It's not like you have to have a paragraph. So what'd you do? Just put a pi in for x and see if that came out to equal 2 pi? I mean, that's really what it is. Is this point on that line? Because this equation should be all the x and y points on that line. So plug pi in for x, work out the right side, see if it equals 2 pi. In this case, I don't think it did. They weren't equal. And so you'd say, since they weren't equal, this point is not on that line. But your work would be a lot of your explanation. Okay? Sometimes that, your work or a picture or something like that is a big part of your explanation. Okay? All right. So, we talked about the questions. We've done exploration 2. There's Appendix B, there's Appendix C. All right? If you have any other concerns, we may have some time here at the end. Remember, there's always a solutions manual that you can look up and check some of your other answers. I encourage you to do that because you might be rolling along. We don't answer and don't go over one you might have had a question about, and you're not sure if you were right. And so, be sure to take advantage of that. All right, let's move on here then, and get out that packet, Exploration 2, what we just did yesterday, and we're going to work on Exploration 3. All right. Now, remember what I said. In exploration, on these explorations, what we're doing is we're kind of getting a little bit of a vision for the future of what this calculus thing is about, what this class is kind of going to be doing. These are not things that will be on your first quiz, right? I mean, these are just kind of big picture, what is it that we're going to be discussing. So, if you look up here on the board, I've got differential calculus over here. I said that calculus kind of split into 2 pieces. The first half is differential calculus, which would be like the door opening stuff, instantaneous rate of change. Okay? Where we take, and we did slope. Now, what was our answer to this? Remember, it was 30 point something? It was 30 point something what? What were the units? Degrees per second. Now, it shouldn't be a surprise that it was degrees per second because what we did was a slope calculation. And if you look at the units on the y and on the x, when you do slope, the y units are on top and the x units are on the bottom. And so our final answer, our slope, should be degrees per second. It's a rate. And instantaneous, because at one point, rate of change, degrees per second. Okay. Now, what you're going to do on this exploration is you're going to investigate the other half of calculus, which is called integral calculus. And it's going to lead you, as you go through the first 4 questions, and we really want to get through the first 4 into the 5th question, and read the 5th question as well. And when you get to about that point, you can get on to 6 if you're ahead. Then we're going to pull back and we'll kind of talk about it together. So you can work on it by yourself. You can get together with a group of 2 or 3 and talk it through. Okay, whatever you want to do. But here we'll take about 10 minutes or so to see how far we can get on that. Okay? Was Natalia here? But she. Again, the key to this worksheet is units. Think about the units, okay, of the x on the graph and the y on the graph. Think about the units.
Basically saying how to. Right here we did it. Oh.
There is kind of a physics. All right, I tell you what, I think most of you have gotten to the point here where we can talk this through. So let's go ahead and move back to your spots. And let's kind of try to tie together here what you've been talking about. I heard some good discussion going on here. And essentially, again, this idea of integral calculus, what does this mean? Well, so we started this problem, and we're just talking about this truck traveling along, and as most of you noticed, most of you in question one, you got 1,200 feet, right? the old distance equals rate times time. Very simple, algebra 1 or even before algebra kind of thing, where you just take 60 feet per second times 20 seconds. Okay? But now, here's where question 2, and then like somebody mentioned physics, because I know in physics you kind of get into this graphing stuff with motion and so forth, and so if you've been in that, that's kind of a nice thing that you can think back to. But right here between 30 and 50, the secret is that the truck is going at constant speed. That's what makes this an easy thing to do. And so in question 2, they say that that's kind of represented by this rectangle. Now, for some of you, if you hadn't been in physics, this would be a new thought. I mean, you would not have thought of looking at a graph and calculating this area. But if you think about it, area equals length times width, distance equals rate times time. I mean, right? I mean, those are actually, in this case, the same equation. Because look what we have. The length, or the width, or height, however you want to call it, of this rectangle is 60, but what are the units? 60 what? Feet per second. And what's the width of the rectangle down here? 20 seconds. And the units are very important. And so if we take length times width, what do we got? 60 feet per second times 20 seconds. Rate times time. Seconds cancel seconds, right? And you end up with 1,200 feet. Now, my daughter, who's in 8th grade and is quite smart, I might be biased, but she would really be freaked out by the fact that we just did area, we just did length times width and got feet for the units. Because what are you usually taught that your units on area would be? Feet squared or centimeters squared, right? When we do units, when you do area, it should be centimeters squared, right? Well, no, not necessarily. Here we just did area, and the units were feet, okay, because of the units of the length and the width. Now, I want you to notice something over here. Compare that to what we were talking about on the degree and the door opening problem. We were saying that, hey, I can do slope of a line. 2 points, do my slope formula, I get average rate of change. But if you want me to do slope at 1 point, I can't do that. So what I will do is take 2 points really close, and I'll estimate what the slope of that line would be. Okay, now you come to this worksheet, and we need to do the area of a rectangle. Now it turns out that this area, this is a velocity curve, and what we've just learned is that if we do the area underneath the velocity curve, it tells us how far the truck traveled. So now you go down to question 3. And question 3 is saying, well, geez, if this area here told you how far the truck traveled in those 20 seconds, then shouldn't this area here tell you how far the truck traveled in those 20 seconds? Does that make sense? Sure. What's the problem with finding that red area? It's not a shape, right? I mean, it's this curved thing. It's not a shape that we know from geometry. We don't know how to find the area of that shape. We have no formula for it. Now compare that to what we did here. You want to find the slope of a straight line? No problem. Pick 2 points, do a slope calculation. But you want to do the slope of a curve. We don't know how to do the slope of a curve. We only know how to do slope of a line. And the best we can do is have a line that touches the curve in 1 point. But then we only have 1 point. How do we do the slope? We said, well, we'll just estimate. Well, look what we got here. We want to find this area. We don't know how to find this area of a curved region. So what we will do is we will do the best we can. We'll do what we do know how to do, which is we'll divide it up into a bunch of squares, and we'll estimate that area. See the connection then between these two seemingly different ideas. So right here, so what integral calculus is really is area under a curve. Okay? It's area under a curve. And that curve might be something like this that we don't have any formula for. So how do we do it? And now remember, this is the second half of calculus. This is stuff we'll be starting to do in February and so forth. But this is just giving us an introduction to it. So anyway, in number 3, you counted the squares, and how many did you get? 28 and a half, or somewhere in there, right? Somewhere in that vicinity, probably. Okay? And then in question 4, they said, okay, but how much is each one of those little rectangles, little squares represent? Yeah, each one of those little squares is 5 seconds wide and 10 feet per second tall. That sounds weird to even say. But 5 seconds wide and 10 feet per second tall. So you take 5 times 10 is 50. You take feet per second times seconds. The seconds cancel. Each one of those is 50 feet. So you take 28.5 squares times 50 feet per square, and you get what? 1425. Now, does that make sense? The truck went 1,200 feet during these 20 seconds and went 1,400 feet during these 20 seconds. Does that make sense? Sure, because in these 20 seconds, he was doing what? He was going faster. He started at 100 feet per second. He was going faster during those 20 seconds. Now, but the difficulty, though, in finding how far, let's go back to distance equals rate times time. The difficulty is his speed was changing the whole time. How do you get how far he went if you don't know how fast he was going? Because his speed was constantly changing. He was just slowing down that whole time. Okay, but he was still going faster than he was here. So he traveled farther. So there you go. So that's the idea of integral calculus. So now we move on to number 6. And of course, number 5 says, all right, that's called the definite integral. It says, how come the units were feet? Well, because we took feet per second times seconds. I mean, that's as simple as you need for number 5. Feet per second times seconds turns out to be feet. Okay? Now, look up here on the board real quick. On the board, look at the connection between rate of change here and area under curve, because what we did here is we took the y units, feet per second, and we multiplied them by the x units. Right? We took the y units and we multiplied by the x units and got this. Look what we did for rate of change. We took the y units and divided by the x units. So again, they kind of have this inverse relationship. Okay? Y units divided by x units gives us rate of change. Y units times x units gives us this idea of area. Okay? All right. So that's definite integral. And so we move on here to do one last problem with it, number 6. So appropriate for this time of year, a little football problem. It says, this graph is a cross-sectional area of a football. Now what that means is, if I took a football and I held it so one end was pointed out at you and one end was pointed back at me, and I went in 1 inch and I sliced it, well, you'd probably go flat. So let's say it's a solid chocolate football, okay? So we're going to take, and we're going to move in 1 inch and we're going to slice it. Now what are you looking at from your end? Yeah, circle, chocolate, right? I mean, you're looking at a circle, right? A little circle, right? So if I sliced off 1 inch, you'd be looking at a little circle. Then I went in 1 more inch and sliced again, what would you look at? A little bigger circle, and then a little bigger circle, a little bigger circle. So you see why this graph is what it is? Okay? You come in 1 inch, and you got an area, cross-sectional area, a little bit. You come in another inch, you got a little more area. Come in another inch, more area, until you get to the middle of the football, and then you got the biggest circle, right? And then you go a little farther, now it's getting littler as you get to the other end of the football. Okay? So that's what this graph represents. A slice taken every inch and measuring the cross-sectional area of the slice. All right, so we're supposed to do the definite integral, which means count the squares. So why don't you do that real quick. So let's do the same thing that we just had to do on the other problem. Let's figure out what the area is underneath this curve. And we'll do it by counting the squares. How many do you get? 44? 45, 44, 44 and a half, somewhere, okay, roughly, right? I mean, it's an estimate. This is about as good as we can do, right? Now, if we wanted it to be a little more accurate, maybe we make little square, right? Littler grid. You know, the littler the grid, maybe the more accurate we could get. All right? But now we got to keep going though. What else do we need to know?
How big each
Each square. Now, one thing I forgot to put on here is my units. What are my units down here on X? Inches. What are my units over here? Inches squared. Because remember, it was the area of a cross section, the area of a slice. So I got inches here and inches squared here, and how tall is one of these squares? 5. So I have 5 inches squared on this side, and I have what? 1 inch on this side. So the area is 5 inches cubed. What is inches cubed? Volume. Okay, so I've got 5 inches cubed in each square, and I got 44 squares. What's that make? 220 inches cubed. What did I just find by doing that? The what of the football? The volume of the football. Look at that. I mean, we just did that area business to find how far the truck traveled, and now we just found the area under that curve to find the volume of the football. Now, somebody in the other class said, why didn't you just dunk it in water and do displacement? Well, you could do that, but it was chocolate who wants to do that. But you know, no, you could, absolutely. Matter of fact, later in the year, in March or April, I don't remember what it is, we're going to do a little lab experiment where we're going to slice up lemons. Very similar to this to find the volume of a lemon. And we're going to do displacement. We're going to do a variety of things to check the volume of this thing. But an engineer who's designing something and needs to know the volume so he knows how many materials so he can do a cost analysis has got to know the volume, and he doesn't even have a real thing. It's just on a computer screen, so he can't dump it in water to do displacement. You have to be able to find volume. And so you can do mathematical modeling like this so that you can figure out those things. So it's kind of neat. We just did area where we got feet as the units, and we did area where we got cubic inches as the unit, right? And so it can mean this area business here can tell us a lot of different things depending on what the graph is that we're looking at. Okay, so we can go ahead and put that aside, and what I want to do here is just review a couple of things that you're going to need for your homework for tomorrow. So if you look at that assignment sheet, you want to take out that assignment sheet. All right. Now, you can write some of this down, not write some of it down, whatever you think you need. But your assignment is going to be Appendix E, which deals with logarithms and exponentials. We're going to review that here real quick. And then Appendix G has a few story problems. Algebra 2 type story problems that they have you set up. You don't have to really solve them, I don't think, but you have to get them set up. Of course, that's the toughest part of the story problem, then get them set up. Right? So there's not much I can do to help you on those, but but I certainly will if you come in, if you try them and you've got questions, you want to come in and see me in the morning or before class or whatever. Now, so let's just review this idea of exponentials here a little bit. And logarithms. And first, before we do that, function notation. So if I tell you, if I write this, if I give you the function f of x equals, oh, let's make it easy, x squared plus c. So let's say I gave you this function f of x that was x squared plus c, and I told you that f of x, or excuse me, f of 2 equaled 1. Okay? And I told you I wanted you to find c. So just from a notation perspective, what's that mean f of 2 equals 1? Plug 1 in for x. Put 2 in for x, because that's where the x is, right? And the y, or the output, now you'll hear me say output a lot instead of y, but the output then will have to equal 1. Okay, so f of 2 will have to equal 1. So we get 4 plus c would equal 1, c would equal negative 3, that kind of stuff. So just some stuff, make sure you're comfortable with function notation and things like that, because we deal with it all year long. Okay, I think this is a good way to show my work on this one. Now, I'm not saying you have to do that much work. I'm sure you could have said 2 squared is 4, 4 plus c is 1. You could have done those at your head, probably. But I do think it's a good habit to get into showing some of this, because as we get into problems, harder problems, it gets pretty important to show that. All right, let's get into exponentials. So if I have b raised to the a power equals c, can somebody tell me what that would be in log form? Okay, right here, this b, let me stop you now. This b is the base, because it's the thing that the exponent is setting on. We call that the base. It's also the base in the logarithm. Okay, of c a. Always remember, in a log, it's this down here raised to the a that equals the c. b raised to the a equals the c. Okay, b raised to the a equals c. You really need to be able to go back and forth between these two forms. Okay? All right. So let's take a look at a problem. So if you had, let's say, log of 81 base 3. Now on the homework, I encourage you to try and not use your calculator at all. Matter of fact, somebody I'm sure is going to come to me, or not very much. Somebody's going to come to me and say, where's the LOG button? How do we do log base 3? We do not do log base 3 on the calculator, okay? We're going to rewrite it as natural log, and if you ever have, I mean, it's on there. I mean, I think you can find it in some of the menus, okay? But if we ever have to do any of these log problems, they're almost always in a no calculator kind of problem. Almost always. So we need to be able to work with them in that setting. So tell me how I find what this is. 3 raised to the what equals 81, right? So, now you could guess and check. Again, I said not use a calculator. Some of these are supposed to come out even. Now, there are some on there that you may use your calculator for. You'll see as we do it through here. But anybody know what that is? 4. It's 4, right? 3 to the 4. So the answer there is 4. Okay? So that's a log problem like that. Let's take a look at another log problem. Let's say we have 2 to the x equals 14. Okay? Now there are 2 different ways that you can do this. Now this one doesn't come out so nice. Okay, there's 2 different ways you can work this. What would one way be? Change form. So let's change it to log. So it'd be log base 2 of 14 equals x. Now, it's probably not okay to leave it like that. In this class we use natural log, which of course is base what? No, that's common log. That's the LOG log. LN is E, base E. We're going to be using LN, natural log, base E. And the reason that's important is a question like this, well, it wouldn't be just like this, there'd be more to it, but on the AP test, where this would show up would be on the no calculator multiple choice. And you might get down to this, and you look at your choices, and that wouldn't be any of the choices. They'd all be natural log choices. Okay? Well, there's a rule, it's called the change of base formula, where you can take any log of any base and change it to any other base by doing this. So we're gonna change it to natural log base E. It would be ln 14 divided by ln 2. Does that look familiar at all? Okay? If it does, great. If it doesn't, that's okay too. But that is what you do with it right there. Now, while I'm on that, I just want to show you the calculator real quick. I had told you guys the other day, we had talked about solving. Didn't I show you that on the calculator, how I could solve equations? Didn't I show you that? See, so, but this is what I don't want you to do on the homework, because this is not going to help you at all. But I could come in here and I could do solve 2 to the x equals 14, comma, oops, yep, thank you. Okay, equals 14, comma, x, hit enter, and look what it does. ln, see how it puts it in natural log also. ln 14 over ln 2. Now, if I'd rather have a decimal, then we talked about this earlier, I can hit control enter, and it'll give me the decimal. But back to our homework, you would just stop right there. Just stop right there. Don't, and so there's no need for a calculator for any of that. Now, here's another way we could solve that problem. And actually, I like this better because I think it's more versatile and it works on more problems, is we can do the natural log of both sides. I use natural log because that's the log we usually work with. So I'm going to do the natural log of both sides. Okay? Now, on the left side, I can use one of the properties, and we're going to review the others. One of the properties of logarithms, you remember this? You can bring the x down in front. When you do a log of something that's got a power, you can bring that power down in front, like this. And that comes in real handy for us throughout the year. And now to solve for x, I can divide by ln2, and just like magic, I get exactly the same answer. Okay? So you can just leave it just like that. So you don't really, again, need to calculate. All right. A couple other properties of logs that I wanted to mention. If you have log, oops, well, it doesn't matter what log. Yeah, we'll do natural log. If I have log of m plus natural log of n, what's that equivalent to? M times n. ln m plus ln n is equal to that. And that's, of course, true for any log of any base. And then if I'm subtracting them, that's the same as a divide. Like that. Okay? So we have that property where if we have a log with a power, we can bring the power down in front. And if we're adding two logs, it's a log of the product. If we're subtracting two logs, it's a log of the quotient. Okay? So those properties, along with the change of base and the switching between the two forms, should be enough to help you work those problems. So I'm going to give you the last 15 minutes here to get started, and I'll help you if I can. Appendix E and Appendix G for the log. Yep. Was that the page you wanted?
Yeah.
Is that the page you wanted?